Hello, this is Robert Murphy again from the University of Colorado, and I am presenting a series of videos on lipidomic strategies sponsored by Avanti. This particular video has to do with problems one might encounter with some solvent extractions, an important first step in all lipidomic studies. So this video presents some of the challenges which you may encounter working with lipids when you extract them with organic solvents, immiscible solvents, and also storing the lipids in these solvents. And it's maybe some advice on what you may be on the lookout for when you're using different solvents. So solvents are an important part of lipidomic studies. They're typically the very first step, as you saw in my introductory video of a lipidomic study. They're not limited to just chloroform, methanol, water extractions like were described by Bly and Dyer or Jordy Folsch. And very often one can tailor your organic extraction to actually optimize the yield of a certain class of lipids and at the same time minimize isolation of an interfering class of lipids which you are not interested in studying and therefore just become problematic to you. The other type of extractions which are out there for lipids are solid phase extractions. The commercial term like SEP packs, which are used extensively to isolate lipids based upon the hydrophobic character or the lipophobic character of lipids compared to other biomolecules which are not retained by these substrates. I might also point out at this point that not all lipids can be extracted by immiscible solvents. Some people think that's the hallmark of the definition of a lipid, but it is clearly not. There are lipids and lipids that we've spent a long time studying, for example, leukotriene C4, which cannot be extracted out of an aqueous system using an immiscible solvent like chloroform methanol. You must use solid phase extractions to isolate that particular lipid from an aqueous environment. So here's an example of an alternative lipid extraction besides the Bly-Dyer, and on the left-hand side here we're looking at the recovery of a triacylglyceride and a phospholipid. By the Bly-Dyer technique, you recover triglycerides very well, and of course they're excellent. They were devised for the extraction of phospholipids. But if you change your immiscible solvent to an isooctane ethyl acetate mixture, you still get excellent recovery of the triglyceride and very poor recovery of the phospholipid, and that's illustrated on these two TLC lanes, and you can see that the phospholipid origin down here is really quite remarkably large compared when you use chloroform methanol compared to when you use the isooctane ethyl acetate. But yet the neutral lipids you may be interested in, the triglycerides, cholesterol esters, very well extracted. So this is a way for you to use solvent extraction to really simplify your next step, and that's a way to analyze these molecules because you don't have the interfering compounds. So that's a very important. This devising your extraction can give a very useful way to optimize an isolation protocol. Okay, let me talk about some problems that you may have with handling with lipids. And these are suggestions that Avanti has come up with, which are really should be taken to heart. First of all solvents contain low levels of contaminants. I don't care which one you buy. There's always going to be some contaminants in there. And some of these contaminants can interact with the lipid class that you're looking at. So one has to be aware of that. You really need to use the best solvents you can buy. And surprisingly, sometimes what you think is the best solvent is not the best solvent. And this sort of feature we'll talk about a little bit because of the presence of some stabilizers, which you may think just add impurities, but in fact are really critically important. The other thing is you always want to use fresh solvents. The problems we get with solvents are often appear with storage of solvents, exposure to light, for example, or someone like that. And so minimizing that by using just fresh solvents is really quite important. I'm going to specifically talk about the problems which lurk in chloroform, methylene chloride, and methanol. Just to give you an example of what can happen, I think other interesting stories can be brought up for all of the solvents. I'm sure everyone is aware of the problems with working with diethyl ether, for example, the forming peroxides. I'm not going to talk about that, but virtually all solvents have their own inherent problems. Okay, so here's the problem with chloroform. So chloroform is typically used for lipid extractions by the method of Bly-Dyer, but it can undergo decomposition reactions catalyzed by the presence of ultraviolet light in particular, and oxygen. And so what you can form from chloroform is this molecule phosgene, a very reactive molecule. Phosgene right here. It can also be catalyzed by iron, for example, here. In Denver, where I live, we have a very high UV flux of ultraviolet light. And so this can really happen if you're not careful with your chloroform and store it in bottles which are protected from light. Now, chloroform does have some stabilizers in it, for example, ethanol. And what ethanol does is it reacts with the phosgene, and so that minimizes the reactive phosgene in doing it. If there's any chlorine present or other halogens, something like aniline, we'll talk about that later, will reduce the appearance of highly reactive compounds like chlorine. Okay, so here's what happens with phosgene. So here's an aminophospholipid I've just drawn here as just the amino group. It's going to do a chemical reaction, quite facile chemical reaction with the amino group, and then another nucleophile reacts with the other chlorine atom to release 2 hydrogen chlorides, and now you have this nucleophile attached. So if you have any ethanol present, you form a carbamate ester. And if you have methanol present, it's a methyl carbamate. And so these carbamates can build up, and you don't want to be confused by these. And a specific example really came from the work of Chris Rates, where he found it reacting with another nucleophile. And that's illustrated here, where here you have 2 mass spectra here. One is an extraction of a bacterial lipid extract with chloroform, and the bottom one is from methylene chloride. Now they look identical in this lower mass region, but up here at high mass we have some new peaks which have appeared which are totally absent in the methylene chloride, and those, after a lot of work, turned out to be the glutathione adducts of phosphatidylethanolamine, and here you can see the carbamate ester with the glutathione tripeptide right here, and so there you can see it there. And so these are artifacts. They were actually initially identified as not artifacts, but possibly biological molecules, but they're artifacts. So this was done by Chris Rates when he was at Duke University. Another example is methanol. Methanol is widely used in all lipid studies, and methanol can contain trace amounts of reactive carbonyls, for example, formaldehyde. So here's the structure of formaldehyde down here, and here's 3 different manufacturers of methanol, and you see they actually tell you how much formaldehyde is present in there. There's another way to get formaldehyde from methanol, and that's if you heat methanol. For example, when you flame seal a tube using glass blowing techniques, you can form methanol. So formaldehyde. So formaldehyde, you see, is doing this chemistry of doing Schiff base formation with the amino group, and that's adding 12 carbons. Which is just carbon, because you're replacing 2 protons and adding just that methylene group from the formaldehyde. So you're adding an adduct to this, and it looks at a different, these adducts appear at a different mass than what you have. So here's a mass spectrum on this slide here of looking at a Avanti product. It's an internal standard that people can use for phosphatidylethanolamine. It is a 17-0-20 with 4 phosphatidylethanolamine, and you see that it's in a glass vial, and so it's the sodium salt which picks up from the glass. And if you don't seal it, you see some protonated and some sodiated species here, but they're really no things 14 mass or 12 mass units different. But if you take a flame and heat the that vial which you're trying to seal, the methanol is a vapor and it's being burned by that flame, forming formaldehyde and dropping back down into the solvent methanol. And here we now see two new peaks which have emerged, plus 13 and plus 35 from the molecular weight. And so these things are the addition of formaldehyde to either the sodium adduct or to the protonated adduct here. And now if you cool the solution before you do heat flame sealing, you can minimize that. So that's how Avanti gets away from these artifacts. And it's an important thing in case you seal your samples by flame techniques. Okay, the other example I want to talk about is dichloromethane. And we purchased this dichloromethane because the student thought, well, this must be the highest quality methylene chloride. It's for HPLC, and there's no preservatives present in this one, so that must be good. As opposed to dichloromethane here from Sigma Aldrich, it contains, as you can see here, maybe 100 parts per million of the hydrocarbon amylene. And so maybe that's not so pure. So this is what amylene is for. Methylene chloride is made by the reaction of chlorine gas with methane. It's catalyzed. And so now you have methylene chloride and hydrochloric acid. And so they purify the methylene chloride away from the chlorine and the hydrochloric acid. And they add the amylene, 2-methyl-2-butene, so that chlorine, which will react rapidly with that double bond, is minimized. And so they tell you halogens to pass tests, whatever that means. They're not telling you exactly what their result was. So here's an experiment which we did with some Avanti triglyceride standards. We were doing this to do a quantitative analysis, so we wanted to have these as reference standards. The 44.1D5 is the internal standard, and we had various triacylglycerides with different numbered double bonds. And so this will allow us to generate a standard curve for these species. So here's the Avanti standard in methyl tertiary butyl ether. We see sort of 2 HPLC peaks, 3 HPLC peaks, not very good. Each one chromatographs quite well, but there's mixtures of these, so they sort of look rather strange. The same sort of thing was observed with LCMS when we used the preserved dichloromethane. But look at the chromatographic trace for the highest quality methylene chloride, non-preserved. They look very different. So what's going on? How did these change? Just by dissolving them. Well, if we look at the individual masses which are coming up in those areas, we see this is now a display of the expected masses we should have and observe for the standards. See, each one chromatographs quite well. They're colored here. The preserved one, identical sort of behavior. But when we looked at the non-preserved, only 2 of the masses appeared, and none of the other ones that we expected, only 2 of them. And the other peaks were totally unexpected. This is what the mass spectra of the standard looks like, just blown out on in a mass spectrum here. And you can see they all have very nice peaks, resolution, double bonds between those 2 standards, quite well indicated. And this is the non-preserved identical behavior. This is the non-preserved dichloromethane. And here we only see 2 peaks we expected, and now we see 4 peaks, which we don't know what they are. It's 841, 843, so where are the other standards? They're gone, they're not here. And what are these new ions that we're looking at here? They weren't in the standard, and we have to put our thinking caps on and figure out what they are. So we did that, and what we found what they are is they're chlorinated adducts of, in this case, the 50 with 1 internal standard has 2 chlorine atoms on it. That's the 920. And then the 841 is the deuterated internal standard, 44 with 1. It's got 2 chlorines on it too. Whereas the other 2 ions, well, they're the chlorine 37 adducts, and there's 2 of them, so they're almost a 1-to-1 mixture. So we also found cholesterol oleate did the same thing with the unpreserved dichloromethane, 2 peaks, because it's got 4 chlorines in it. of all things. So it's not mass 668, it's mass 808. So it turns out that unpreserved dichloromethane had chlorine present, and that chlorine was adding to double bonds in the lipids that were present here. So, in summary, pay attention to what solvents you're using. Chloroform widely used, but be careful of phosgene. Sometimes you get a bottle which has phosgene already in it, or if you store the chloroform, you may generate phosgene. Methanol it does contain formaldehyde, trace amounts of it, which can form Schiff bases with aminophospholipid. Sometimes you can generate that yourself. Methylene chloride may contain chlorine, particularly if it's unstabilized in terms of doesn't have the sacrificial olefin in there to react with chlorine to remove the chlorine which is present. And so that chlorine can add 2 chlorines add for each double bond, so that causes quite a change in the molecular weight of the molecule, especially like our standards had sometimes, some of them had 4 to 6 double bonds. They were way above our scanning mode of that mass spectrometer, so we didn't see them. So there can be pitfalls that you must consider with using solvents. And in the beginning part of this talk, probably thinking about what solvent system you're using to extract lipids can pay very good dividends to you in your final analysis.